Yeah, so in the previous video, we discussed the three different categories of feature selection, namely the filter methods, the embedded methods, and the wrapper methods. Now let's dive a little bit deeper into one of the categories, the filter methods. And then, of course, in the upcoming videos, we will also talk about the embedded methods and the wrapper methods. But yeah, now the star of the show here of this video would be the filter methods. So what are these filter methods again? So yeah, like we discussed last time, so filter methods are essentially focused on the intrinsic properties of the feature or features. And this means essentially that we are using properties or measurements of the features themselves, and we don't really use a model here for feature selection. So one example we gave last time was the variance threshold. And I wanted to zoom in a little bit more into this variance threshold and discuss how it works. So when we use a variance threshold for feature selection, how that works is essentially that we compute the variance of each feature, and we assume that features with a higher variance may contain more useful information for training a classifier or a regression model. So why is that true? Why would a feature with a higher variance contain more information? So I try to sketch it here at the bottom, where let's assume we have a feature called x1. And here on the left-hand side, these little diamonds shall represent different training examples. And yeah, we can see here on the left-hand side, this would be a feature with a high variance. And yeah, across the feature axis, the features are pretty much well spread out here. So here in this case, we have a feature with a high variance, and on the right hand side, we have a feature with a low variance. So in this case, the feature is less spread out. And you can maybe already see why a higher variance might be better, because it allows us to construct decision boundaries based on that feature. So yeah, let me illustrate this in a little bit more detail. So on the left-hand side, I have again my feature with a high variance. And note at this point, we don't really look at the target variable or the class labels. But let's just assume for the sake of the example that we have a binary classification case where we have the two classes. One is class square and one is class star. So we have these two classes here. Class 1 and let's say class 0 and class 1. And then there are potential scenarios. So of course, the best case scenario would be this one, where all the data points from one class are on one side, for example, the square here on the left-hand side, and all the data points of the other class are on the other side. So in this case, it will be very easy to construct or find a decision boundary that separates the data perfectly. And but of course, this is not always the case, and it could be also here in this worst case scenario where we have alternating class labels across this feature axis. But again, still, if you think about a decision tree, we would still be able to construct decision boundaries as long as the features are well spread out. So the worst case really is if features overlap, because if features overlap, they don't really give us any useful information about the class label in the context of making predictions. Yeah, since it has been quite a while since we talked about decision trees in the very early lectures, here I have a coding example to show you really that a decision tree would be able to classify these data points perfectly. But also note that perfect classification here on a training set does not imply that this model would generalize well to new data. So that is a kind of like a separate problem. But yeah, just for the sake of this example, assume we have the feature values 1, 2, 3, and 4. So 1, 2, 3, and 4, just some arbitrary feature values. And then we have the labels 0, 1, 0, 1, where this is my feature array and this is my label array. So then I'm fitting my decision tree here. I'm not limiting the depth at all, and we just fit the decision tree. And then we can see based on the score function that we get a 100% accuracy on the training set. Again, like I just mentioned, 100% training accuracy does not imply perfect generalization to new data. But it's just like illustrating that a feature with a large variance can be useful for distinguishing between different classes. So here at the bottom, using the code that we've seen earlier in earlier lectures, we can see that on the right-hand side, the decision tree is perfectly able to distinguish the classes. So we have classes from class 0. So these are my squares. And then we have here class 1, which are my stars. That is probably the worst star I've ever drawn, but doesn't matter. You know what I mean. Okay, so just an illustration that a feature with a large variance can be very useful for a classifier because it's helpful for constructing these decision boundaries. Yeah, now that we learned that the large variance is actually good, we haven't really discussed how we can use the variance as a measure for feature selection yet. So to get a little bit closer to answering this question, let's briefly take a detour and look at how we calculate the variance or how we define the variance. So here is a definition of the variance of a discrete random variable. So a random variable that can take on fixed values like 1.1 or 2.0 and so forth. And how we would define the variance of such a discrete random variable that takes on fixed values is given here. So what we have here is xi. So the xi's are the values that we can take on. Or let's write this maybe as potential value x1 and x2 here. And we subtract the mean here. And then we take it to the power of 2. If we do that, notice that these values can only be positive, and as a consequence, the variance can never be negative, right? Because we are summing here over positive values. So there are here the different values, 1 to n, that the random variable can take on. And there's also this pi here, which you can think of as a weighting term. So like how likely is it to observe a certain value? If each value is equally likely, this would be essentially 1 over n as the p, because it would sum up to 1. Okay, so this is more like the formal definition of the variance of a discrete random variable. In practice, we are usually given a data set with certain observation. And usually we also don't know how likely it is to observe a given piece of information in a data set. So which is why we usually assume uniform weights. Uniform weights, or p equals 1 over n, like I mentioned before. So here at the bottom, this would be then how we would actually concretely calculate the variance for a given data set. And yeah, also note that this would be computing the variance for the population, but typically we are given a sample. So there's also a little correction term. So usually in the denominator, we have the n-1, I think it's called Bessel's correction term, which I'm not going to derive in this video. That could be a good topic for a different video. But in machine learning, just to be honest, no one really cares about that. We have very large data sets in practice anyway, so this becomes kind of like not very important. So in this case, it's like an optional thing to compute the sample variance, but in machine learning, usually most people I know compute the variance like this, even for the sample. This is also maybe partly owed to the fact that when we use NumPy and type np_var, this is also computing the population variance. So if you want to compute the sample variance, you have to change it to delta degrees of freedom equals 1 here. But again, this is a minor distraction here. I don't want to go into too much detail here. I think I explained this earlier in this course when we talked about standardization. Okay, moving on. So for reference, here again, how we calculate the variance. And I wanted to highlight one special case. So where variance-based feature selection is actually pretty useful in practice. So this is the case where we have a categorical feature or a feature with categorical values, and we perform usually a one-hot encoding to construct the binary variables or Boolean features. So each of these binary variables, for each data point, we can observe a value 0 or 1. So we can think of this as a Bernoulli variable. And if we have a Bernoulli variable, we can compute the variance as follows. So p times 1 minus p, where p here is the probability that it is 1, right? So in this case, if you think of a coin flip where you have unbiased coin, where you have a fair coin, then p would be equals to 0.5. And yeah, in this case, if we have knowledge about that, how likely it is, let's say that something is 1 or 0, we can compute the variance generally like this. And just to have a little demonstration of that, so if I use my regular variance computation here on a variable that is equally likely to be 0 or 1, so here I just generated an array with 50 zeros and 50 ones, I get a 0.25. And if I would just plug that into my Bernoulli variable variance calculation, I would get the exact same value. So why is that useful? We can actually use that to kind of like come up with an intuitive threshold for selecting features based on a variance threshold. And I'm going to demonstrate how that works in a moment. Here, just as a small side note, so there are several different filter-based methods in scikit-learn that allow us to perform a filter-based feature selection. And in particular, we are going to look at the variance threshold function here, or class, which allows us to remove all features with a low variance. Okay, let's now put these two types of information together. So we have the variance threshold class in scikit-learn, and we just learned that the variance of a Bernoulli variable is p1 minus p. So how does it help us to select features based on the variance threshold? So imagine we have a data set where we performed a one-hot encoding. So we have n data points, and we have different features, x1, x2, and so forth. Let's just for simplicity look at one of these features. So after the one-hot encoding, these would be features where we have values 0s and 1, right? And there are some of them where we have more than 80% have, let's say, ones. More than 80%. And there are other ones where more than 80% have zeros in that column. And I mean, this is a hypothesis, but we might argue if most of the values there are similar, it's likely not a super useful feature because the values are the same for each data point. So using just this feature alone, I can't distinguish between those data points where all of the data points have the same value, right? So in that kind of thinking, we can then say, yeah, maybe let's just remove that feature. So using a variance threshold, we can basically accomplish that. And how does the Bernoulli variable variance come into play here? So this allows us, to specify how many of the labels should be similar or not. So for example, if we say we want to eliminate features where more than 80% are similar, for p, I can then plug in, let me use maybe the red color here, I can plug in 0.8 and then have 1 minus 0.8, and I should get as a result 0.16. So 0.16 could be then my variance threshold to remove feature columns where more than 80% of the labels are the same. So this would, by the way, work if I plug in 0.8 if I focus on the ones. But similarly, you will notice if you plug in 0.2, 1 minus 0.2, you would also get 1.6. So this is kind of symmetric here, whether we have a 1 or a 0. So whatever we plug in, if let's say less than 20% of the values are a 1, or if more than 80% of the values are a 1, we would drop this feature. So how does it work, let's say, in scikit-learn? So here I'm showing you an example. So here we are importing first a one-hot encoder, and I'm just encoding a categorical variable that has different values: blue, green, blue, green, red, blue, green, and so forth. And I have some class labels assigned to it. I'm not using the class labels at all, by the way. It's just for illustration purposes. And so what I'm doing here is first I'm encoding this categorical feature X into a one-hot encoding. And I'm also dropping one of the columns because it would be redundant to have all the columns there, because one column can be deduced from the remaining columns, as we have discussed in an earlier lecture on one-hot encoding. So here I'm using my transform method, and then because by default, to make things efficient, scikit-learn has so-called sparse arrays, as we discussed earlier. So it's just like a more efficient representation, but we can't really print sparse arrays because it would not be very easy to, let's say, deduce what values are contained, which is why I'm using the toArray method here to display the output here as numbers. And I'm also, by the way, including the code in the description of this video. So if you want to toy around with that, there should be a link to the code example. I have everything here in a Jupyter notebook. Okay, so this was just the setup for the one-hot encoding. And next, let's get to the core here using the variance threshold class. So here we set the variance threshold, and we set a threshold of 0.16, which we compute like we did before. 0.8 times 1 minus 0.8, so such that if we have a variable where more than 80% of the labels are the same, they are removed. So here I'm applying this to my one-hot encoded array, and you can see then only one column remains because this column here gets removed. So this would be the column if we would actually trace this back to the features here. There is only one instance of red, which corresponds to this one here. And this doesn't really help us to distinguish between different training data points. So in this case, it's a feature column that we remove after the one-hot encoding. Okay, so this was a very long explanation on how we use the variance threshold, and we were using these one-hot encoded variables as an example. But of course, it's not just restricted to one-hot encoded variables. You can use the variance threshold for any type of variable. All right, coming to a conclusion now. So what have we learned about the variance threshold? So first of all, the variance threshold is about computing the variance of each feature. And we assume that features with a higher variance may contain more useful information. We can use that information then to select subsets of features based on thresholds we as the user specify. So we can, for example, say keep a feature if it's greater than a threshold. Or we could also just compute the different variances for each feature, and then we just select the k features with the largest variances. And what's one advantage of using this technique? I mean, one really big advantage is that it's a very, very fast technique. I mean, computing the variance on a single feature is usually super fast compared to anything else that you will encounter in terms of feature selection. But the bad thing about this is it does not take the relationship among features into account. So we are really just looking at one feature at a time. It doesn't really tell us much about, let's say, how this feature is correlated to our target variable. And it also doesn't really tell us about whether this feature is redundant or not based on similarities to other features. And it doesn't tell us about how well, let's say, it helps the model to achieve a high accuracy on, let's say, the test set. Okay, so we will then in the next video see some alternative techniques for feature selection, namely the embedded methods and the wrapper methods.